welcome to Chemistry 111. We're just note that we are well ahead of the notes. If you look at the syllabus, the plan for this week was to start chapter 4 with the idea of finishing it next week. So we are on the last slide of chapter 4. We're going to start by a quick review of chapter 4's material, finishing this, looking at some of the homework, and maybe starting a bit of chapter 5. Assuming I get the test from everyone today, or by tomorrow at the latest, on Friday we'll go ahead and go over the crib for the 2 tests. But that test is due today for full credit, and obviously 5-point penalty for every day late. But just heads up, so be thinking about that, whether you need to email it to me or turn it in person, however you want to get it to me, try to get it to me today. Okay, chapter 4. We started out with the basic concept of electrical energy. The whole idea that the electromagnetic frequency, that light, among other things, is a form of energy that all travels at, the speed of light, 2.988 times 10 to the 8th meters per second in a vacuum, and has various speeds in other media, but it's very fast. It's full of energy, and it can be described by both a wavelength and a frequency. We started by talking about how light and those wavelengths and frequencies were interdependent. They were related by equation. And then we further talked about how we could determine the energy of a frequency based on another equation. But eventually we got to relating it to, if light has a wave-like and particle-like nature, does matter have that same wave-like and particle-like nature? And the answer was yes. And we eventually used some of the weird properties of light and how it interacts with atoms to try to understand how the electron cloud is situated. We just went on to describe various orbitals or energy levels where the electrons could be situated within the electron cloud. We talked about how to write an electron configuration. We talked about how to do both full electron configuration and condensed electron configurations. And finally, we talked about how to do a electron configuration of an ion. This last slide, it's not much. It's just a kind of a review of all the different ways we designated these electrons. Now, I was looking at the homework, and I think I've removed any question about this, but so we got to think about this. There's maybe one question that is somewhat similar that uses this idea. That when the Pauli exclusion principle, which is one of the principles of putting electrons, is that no two electrons can have the exact same designation. No exact same N, L, M sub L, and M sub S. 2 electrons have to have at least one of those numbers differently. As long as that's true, it's a valid configuration. So each shell, subshell, and orbital is described by these quantum numbers. When put together, they perfectly describe where the electron is in the cloud. Now that doesn't actually pin down the electron to an exact location, but a whole probabilistic region where it could be. Like it could be somewhere on the surface of this shell that looks like a giant rubber bouncy ball. It's like a little ant walking on a basketball. It could be anywhere on that basketball, but as long as we say it's on the basketball, it's somewhere on that surface. And we can know an approximate region where it's at. But so We started with the principal quantum number n, which was just the energy level. It was any positive integer, and typically for an atom, n, the highest available n related to the row number. Row 1 only really had n of 1 available, n of 1 filled. Row 2 had a n of 1 and n of 2. Row 3 had n of 1, n of 2, n of 3. Now, the next one, which is the angular momentum, L, was describing the shape. This was any integer ranging from 0 to n minus 1, meaning that as we went down in rows, if we went from row 1 to row 2, more shapes, more subshells became available to us. So row 1 only has the S. Row 2 has both S and P. As we move our way across the table, we can see what lithium and beryllium in the S, boron, carbon, nitrogen, oxygen, fluorine, neon on the P. And as we keep moving down, more subshells became available. Then we had the magnetic quantum number, which talks about the degeneracy in the 3D positions. And this ranged anywhere, an integer anywhere from negative L to positive L, with 0 in between. So the subshell S only had one possibility because 0 can neither be positive nor negative. P had 3. E had 5. F had 7, because we're adding 2 new possibilities with each subshell. And then finally, the one we didn't really cover much was the magnetic spin, the spin quantum number, which dealt with whether the electron was spin up or spin down. And we could designate that with positive a half or negative a half. But all these fit together with the Pauli exclusion principle that no 2 electrons can have the same 2 things. Okay. So that's not the end of the world if we don't memorize that. That's fine. Because honestly, that's kind of confusing. Close that out. But that's the end of that chapter. So the first thing I'm going to do is we're going to pull up Achieve, and we're going to look at some of the homework problems, the wide variety that we have. So the first question, like question number 2, I'm going to jump around a bit, but I'll go ahead and cover a decent amount of them. There's only 10 questions on this chapter 4 assignment, so it shouldn't be too hard and too busy. So let's look at the math, and let's look at how we do the other ones. The wavelength of some yellow light is 580 nanometers. 580 nanometers. So let's write that down. Lambda equals 580 nanometers, and they want to know what is the frequency in inverse seconds. So writing that down. Go into the doc cam. Always go into the doc cam. Our equation is C equals lambda nu. C is our speed of light, 2.98 times 10 to the 8th meters per second. So in order to find frequency, we're going to say C over lambda equals frequency, or nu. Now, however, if we look at the units, 2.998 meters over seconds, now divided by 580 nanometers, we got a problem. Nanometers and meters are not the same unit, and thus they cannot cancel out. So one of the things we will always have to do is convert nanometer, the unit of wavelength, into meters. Maybe you'll be lucky and you're dealing with a radio wave that's in meters or whatever. But most of the time, you're going to have a really small number, and this is going to give us a really big number. So you got to remember our prefixes. Milli is 1,000. Micro is 1,000,000. Nano is 1,000,000,000. Nano is smaller than is small, so there's 10 to the 9th nanometers in 1 meter. Now doing that, nanometers and nanometers cancel out here. Meters and meters cancel out here. Setting that up, I can then just simply punch that in. 0.998 times 10 root 8 times 10 root 9 divided by 580. Doing that, you should get a frequency equals to 5.1, we'll say 7, times 10 to the 14th inverse seconds. That's a big frequency, but that is not an unreasonable frequency. That is not an outrageous number. So try plugging that in. 5.17, 10 to the 14th. Now, as I said, you may have a slightly different number. You may have a slightly different frequency to deal with. However, same general idea. Same general idea. You're going to take the speed of light, which is constant, and divide it by your frequency and multiply by number to turn it into from wavelengths into frequency. Turn it into the nanometers into meters or whatever. Now the next one, a certain shade of blue has this frequency in hertz. What is the energy of exactly one photon if this is Planck's constant? So the only thing they give us is frequency 7.3 times 10 to the 14th hertz. Well, 1 hertz is equal to 1 inverse second. Things a little bit easier. The equation is E equals H nu. They give us H is 6.626 times 10 to the negative 34th joule seconds. So, once again, always coming back to the doc cam because I'm going to try to make this as workable as possible. So, 1 hertz is equal to 1 inverse second. So, we can simply plug this into here. And that's going into here. So our 7.3 times 10 to the 14th is going to be greatly reduced in the size because we're multiplying by H, which happens to be really, really small. So a really, really big number becomes really, really small. And because this is inverse seconds, this cancels out with seconds, and we're left with just joules, a form of energy. The hardest part here is just making sure everything is on the right factorial. So 10 root negative 34 times 7.3 times 10 root 14 gives me the answer of, we'll say 4.8 times 10 to the negative 19th joules. So a big number times an even smaller number gave me a net change of a small number. Slightly smaller, but smaller nonetheless. So just notice I plugged those numbers in. I did the multiplication. So 4.8, sure, 4.8. It's okay that this is a really small number because this is energy of 1 photon of light. Not like a flashlight that's shining continuously, but boop, you shot a laser for not even a millisecond, and 1 particle of light hit the detector. And we said how much of that is absorbed. Now, this is the question. Question 4 is the one that is most like the quantum number stuff. Which subshell designations are possible and which are impossible? So what it means to be possible is which ones physically exist. It doesn't specify what element, but you got to think about what are the designations. We have energy level N. Then we have shape L, which has to do, it goes anywhere from 0 to n minus 1. Anywhere from 0 to n minus 1. So let's look at 2 of these. 3s. Is it possible for something to have a 3s orbital? Well, if it exists on row 3, sodium and magnesium would easily be filling the 3s, as well as aluminum would have an electron in the 3s as well as the 3p, so that's very possible. But 3f, is that possible? 3f, well, the rule is it goes anywhere from 0 to n minus 1. If row 3 has available 0, which is S, 1, which is P, and 2, which is D. F would be 3. Possible? No, because shape 3 is not available until you get to row 4. Where does lanthanides and actinides show up? Row 6, but it's row minus 2. So 3f is physically impossible. Another one, 0p. Is there any energy levels of 0? No. Just as there's no row 0. 4f is possible. But 2d, the same reason that 3f is impossible is 2d is impossible. Because if you're on row 2, you have available only the s and the p orbitals. And so 2d is impossible. And that's what that means. Say, looking at kind of the quantum numbers and how those get. How many electrons does each need to fill? We're not looking at the row, we're looking at the shape. So with the s orbitals, how many electrons can be filled into the s? Well, 2. How many electrons can be filled into the 2s? Another 2. How many can be filled up into the 3s? Another 2. How many can be filled in the p? Well, just 6. Because there's 3 p orbitals, there's 6 elements over in the p group. You can fit 6 electrons. So just looking at a few more of these. So this one, look at the ground state of chlorine. We did this one. So chlorine has 17 electrons. So we'd go 1, 2, spin up, spin down. 3, 4, spin up, spin down. 5, 6, 7, 8, 9, 10. So you may have a different element. So, and then 11, 12. And here's the one we actually care about. So we have 5 more electrons to place. So it would be 1, 2, 3, 4, 5. So it would be 2 sets paired and 1 set unpaired as we look at this. So if you had, say, instead of chlorine but sulfur, you would have everything the same except for that last row. The same except for that last row. Here's a good one. Identify the atom with the ground state electron configuration shown. So we're looking at the 3s2 3p1. That tells us instantly we're dealing with row 3, and it has 3 electrons in row 3. So working our way across on row 3, sodium, magnesium, aluminum. So that's the third element in. The first element into the p row. So that's going to be just Al. So just looking at that. So be able to go from electron configuration to valence shell to element, and element to electron configuration. So phosphorus. So how are you going to pop this in phosphorus? Phosphorus is the third element into row 3. So what do you have to do? Since it's the full, you have to write all of them. So I'm going to work my way across. So starting with row 1, I'm going to run S superscript 2. That finish up row 1. 2 S 2. That finishes up to beryllium. 2 P 6 gets me up to neon. That finishes row 2. Then we're at 3s 2 gets me up to magnesium. And then finally 3p. There's 3 elements in to get to phosphorus. So 3p3. So you just got to make sure you superscript things. So phosphorus is letter P. It's on row 3 in the column 6A, I think. No, 5A. Column 5A. Third element in. So that's in the P grouping. That's third P, 3P3. Third row, P grouping, third element in. So it doesn't matter what element I give you, you should be able to do that. Maybe you're going to get phosphorus and you'll be lucky. But it shouldn't really matter. Now for the condensed electron configuration, oh God, they gave me aluminum again. So that'll be easy. So starting from neon's in brackets. So starting from neon, after neon, it's 3s 2. Oh, geez. 3s 2. And then P1. The only difference between full and condensed is essentially we're starting from the noble gas the row before, and we're just doing that last row's worth of stuff. I don't think we have an example of the ion version on here, but be able to do the ion. How do we do ions again? We remove electrons. We remove electrons from the P, then the S, and then the D. Remove electrons from the P, the S, and then the D. But this is the only one that's maybe somewhat tricky. You got to think, how many electrons does cobalt have in the 3D subshell? So cobalt has 5 degenerate orbitals in the 3D subshell. How many electrons does it have? So cobalt is right there on element number 9. If you subtract out your S, that puts 7 electrons. It's the 7th element into the D subshell. 7 electrons. So it's going to ask you how many electrons? going to be 7, but then ask you how many of them are unpaired. And here's where I've drawn out my little thing to make it a little bit easier. So 7 electrons. I got to put 7 electrons in here. There's many different ways you could do this, but there's only one way that gets it right. So we're going to start by putting 1, 2, 3, 4, 5, and then I start pairing them. 6, 7. So how many unpaired electrons do we have? 3. I could have done this, and this would have been wrong. I could have done 1, 2, 3, 4, 5, 6, 7. That would have been wrong-o. So we want to fill in 1 orbital each before we start pairing. 1 orbital each before we start pairing. So the last question is, number of unpaired electrons is 3. Now I could ask you easily any of the ones as long as they don't fall under the realm of the exceptions. I'm not going to ask you for the exceptions on the test. That is beyond what I really want to do. Because, I mean, the exceptions are interesting, but that is neither here nor there. That is more inorganic chemistry. We are focusing more on the straightforward standard stuff. So, I'm going and opening chapter 5. We've practically done all of the chapter 4 homework, so if you've been paying attention, you have all you need to know to answer all these questions. Get that done. In fact, we'll be doing a lab about that like next week or so. Next week will be, the first thing we're doing is you'll look at some line spectrum of some gases. Then we'll be burning some chemicals in a flame to see the excitation colors. Then finally, we will be looking at a UV vis, a visible spectrometer to look at what wavelength was absorbed and what wavelength was observed. I mean, like, what colors does this observe when you shine a white light on it? So, now this next chapter is also very low math. Very low math. So this coming test is going to be more about theory than math. So we'll probably have another test before you know it. However, it shouldn't be nearly as bad as, say, if math was your weakest point. This one should be a little bit easier. So this chapter is all about understanding more of what we learned about why the elements are lined up like they are. Why the periodic table looks so funny, why it is arranged so all the noble gases are right over there. Why does this electron configuration kind of matter? So we're learning about properties of the elements. So, quick reminder, the valence electrons are going to be the thing that controls the reactivity of all elements. And it's going to be useful for understanding the reactivity patterns among the various groups. Typically, any of the core electrons will not react. It's too much energy to remove a core electron. But the valence electron are going to be relatively easy. So looking at the group 1A alkali metals, lithium has 2s1. Sodium has 3s1. Potassium has 4s1. Rubidium, 5s1. cesium-6s1. Each will have a 1 valence electron to lose. And when it does, it'll lose as 1 electron to form an ionic compound. Looking at halogens, group 7A, halogens 2s2, 2p5, chlorine 3s2, 3p5, bromine 4s2, 3d10, 4p5, krypton 5s2, 4d10, 5p5. They essentially have, between the s and the p electrons, 7 valence electrons. In order to get to 8, they will typically gain 1 electron when they form an ionic compound. When they do this, they're going to form the noble gas electron configuration. The noble gas electron configuration is the S2P6 setup, where the magic number of 8 is achieved. The magic number of 8 is achieved. That is one of those numbers we learned that we're going to try to get to. This is extremely stable, and it's why this often happens. If you were to look at transition metals, the magic number is 18 because you're adding those 10d electrons. But we won't really worry so much about the transition metals. But we're going to use this to look at atomic size. We're going to use this to look at how the electrons are lost and gained, and among other things. And this is going to be something that is going to be useful if you have to take any degree of organic chemistry. You have to be able to think about, what does it mean to be electronegative? What does it mean to be a big atom versus a little atom? What does it mean to have electropositivity or electronegativity? All these things will control reactivity on an organic level. But when we look at atomic size, it's never the size of the nucleus that really matters. It's the size of the electron cloud. The nucleus is but a tiny fraction of the portion. Since the Super Bowl is so recent, the nucleus is the quarter from the coin toss, right in the center of the stadium. The electron cloud is expanded out to be the whole arena. So that coin, even if you have a dozen coins in that center of the arena, it's still but a small fraction of the total size. So atoms and ions are all determined about the interaction between the electrons within the cloud and that nucleus. One thing we got to remember as we talk about this: opposite charges attract, like charges repel. So electrons are attracted to the positive nucleus. Electrons are going to repel other electrons. When we increase the charge size, we increase the attraction or repulsion. And there's also it's inversely proportional, that as we decrease the size, we're going to increase the strength. The closer you get, the stronger the effect. So as you get closer and closer, if you ever bring two magnets close to each other, they start maybe weakly attracted, and as you bring them closer and closer, the traction strength gets bigger and bigger because they're becoming closer and closer to the magnetic field's effect of each other. The first thing we have to understand is effective nuclear charge. And that's going to be related to size, among all other things. Effective nuclear charge is essentially how well does the nucleus affect the electrons. Typically, in most multi-electron atoms, typically, most atoms have the same number of protons as electrons. If they all felt the nucleus the same, there would be no differentiation between, say, lithium and fluorine. Lithium, which is very positive, fluorine, which is very negative. Lithium has 3 protons, 3 electrons. Fluorine has 7 protons. Well, no, sorry. It has what, like 9 protons, 9 electrons. They're in a 1-to-1 ratio. If all of them felt the same, if all of them had the same effect on each other, then clearly there would be no differentiation. However, in most of these systems, electrons do not equally feel the attraction from the positive nucleus. That basically, remember, the atom is like an onion. As we put in more electrons to the shell, you start building these shells on top of each other. You have these layers. And these core electrons are essentially shielding the outermost electrons from the nucleus. We're putting a layer of protective electrical shielding from the core to the outer shell. So the core, which is the effective nuclear charge, Z, which is how many protons we got. Well, the Z effective is how well does the outermost shell feel that? Well, Z effective could be the charge minus the shielding effect, the screening effect. How well do these other electrons block out the core? Now, there's actual rules to mathematically calculate this. We will not really use them. We can make a rough estimate, but there's actual rules. The rules were that essentially every core electron shields by a factor of 0.85. So it's 85% effective at blocking out a proton. Not perfect, but pretty good. However, when you get to the same energy level, valence electrons block out only 35% of the core. So all electrons within the valence level do a poor job of blocking out the core from other electrons on the same level. The core blocks out really well, but the valence doesn't block out really well. So we see as we go up within a valence level, the Z effective jumps up precipitously. However, when we go down a row, the Z effective only goes up a bit because we're adding another shell, another set of core electrons, and starting a new valence level. So essentially, as we go up in principal quantum number, as we go down, the shielding is approximately 1-to-1. But as we go across the table, each additional valence electron will poorly shield. So what we see here is a comparison to Z effective and actual atomic number. Hydrogen has a 1-to-1 ratio. They're exactly the same because hydrogen has no electrons to shield from the core. It's 1 electron, 1 proton. There's no shielding. Helium has 2 electrons and 2 protons. So one of those valence electrons shields the other, but not very well. So if Z effective is that, if Z is the purple, the kind of magenta purple, Z effective is that light blue. It's dropped a little bit. Now lithium, 3 electrons, 3 protons. Z effective is Z is 3, but Z effective is close to, say, like 1.5, 1.1 1.25. It's greater than hydrogen, but less than helium, because we now have 1 valence electron that's shielded by a core of 2 electrons. The trend is that magenta is going to always go up by 1. But as we see, we start a row, boom, boom, boom. It's going to slowly build up till it gets to the noble gas, and then it's going to drop down by a bunch. because that noble gas is all valence, and then suddenly that valence becomes the core. That core now shields the new valence. Notice sodium is greater than lithium. It might even be greater than beryllium, but it's still the lowest for that row. And it's going to build up again, dun, 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 until like argon is maybe a little bit higher than neon. Each row is a little bit higher than the last, but not that much higher. So as we build up, as we go across the table, the elements feel the nucleus more and more and more until we start the row again. And then it fills it more and more and more. So these electrons are being controlled by how they feel that row. And how is this going to relate to atomic radius? So remember, protons attract electrons. The electron cloud is where the size is at. So if we have a greater nucleus, a greater magnet in the center, the cloud is going to be pulled in tighter. We're pulling in, you have a greater strength, a greater vortex energy that's going to suck in those electrons, get it closer and closer to the core. The greater Z effective, the more we're going to pull those electrons in. So if you remember, as we go from left to right on the table, the Z effective was going up. So hydrogen has a size of like 37 picometers. Helium has a size of 31. Looking at lithium, we're having 152, followed by 112. Boron is like 85, then 77, then 75, then 73, then 72, then 71. The size is decreasing as we go across the table. Sodium, one is at 186, 160, 145, so on and so forth until we get to argon, which is 98. We see each time we're going up, we're going across the table, size is decreasing because we're having a greater Z effective as we move across the table. However, you should notice as we go down the table, size is going up. 37, 152, 186, 227, 248. Yet back here, we said when we looked at helium, lithium, sodium, the Z effective was going up still. Z effective was going up as we went down the table. But Z effective doesn't go up by much. Z effective doesn't go up by much. And what do we have when we go down a row? Each time you go down a row, you're adding another layer. Even though the effective nuclear charge is going up, we're still adding another layer. It's like we're building a stadium around the previous stadium, a bigger stadium. Even though there's greater attraction, that attraction is not completely offset by, does not completely offset the extra layer of electrons. So each time we add another layer, we're seeing the size go up. So I just want to go to a drawing real quick. Remember, essentially here, as we add, so we have the nucleus, we have the 1s. Even if this is being drawn in by the nucleus, as we add another layer, it's still going to be further out. Even if this is drawn in further, it's still not quite up to where this was at. If I add another layer, even if this is drawn in further, it's not quite drawn into where we started from. So even if the Z effective is greater, it's not counteracting the fact that each shell is further out. Each shell is further from the nucleus. So that effect is going to lead to the trend that we see. The trend that we see is that as we move down the table, size of the atom always increases. As we move across the table, size of the atom decreases. So meaning the smallest atom is in the upper right corner of the table. The largest atom is the bottom left corner of the table. So francium is as big as it's going to get. And helium is as small as it's going to get. And that's where we're going to stop for now. We'll go ahead and pick up again. Well, if I get all the tests, we will go ahead and it will go ahead and pick up the notes. We'll go ahead and do the test, review the test if I have them all. And if we still have time, we'll continue with Chapter 5. If not, we'll pick up on Chapter 5 on Monday.